Greetings, everyone. Well, at this point, we have now developed 3 of our math models for our energy storage mechanisms. We know that the elastic potential energy can be calculated by using 1/2 times the spring constant times the elongation or compression squared. That's 1/2 kx squared. Our gravitational potential energy is mgy, mass times gravitational field strength times height. And after the last lab, we now know that our kinetic energy is 1/2 mv squared, 1/2 the mass times the speed squared. So the only energy storage mechanism math model we don't have is dissipated energy. And unfortunately, it's really hard to make a lab that will work well to figure out EDIS. So I'm just going to try to explain this one to you. It's one of the few times this year when I'm just going to state an equation more or less and not actually figure it out experimentally. So first of all, let's think a minute about what might affect the amount of dissipated energy. And remember here that we're talking about energy that is dissipated because of frictional effects. And we're going to neglect certain things like air resistance and other kind of more complex frictions. We're going to mainly deal with the friction of surfaces that are sliding against one another, that are rubbing against one another. And storing energy is thermal and sound and things like that. Well, since this is the amount of dissipated energy because of friction, one of the quantities that might affect that amount is the amount of friction. And that, of course, will depend on the types of surfaces and the normal force, if you remember the equation. The other one's not so obvious. What else might affect how much energy is dissipated? Well, the other thing is the distance over which that friction acts. Think about if you were pushing a box across the floor. If you pushed it halfway across the room, you would dissipate a certain amount of energy. But if you pushed it all the way across the room, there'd be more rubbing going on between the box and the floor, and therefore more energy dissipated. So the distance that you move that box or slide that box is also going to be a factor. Now, as you might imagine, the equation is really just the straightforward force of kinetic friction times the distance. A couple of ways that I can kind of explain to you why that might work. The first one is, well, look at the units. Force of friction would be in newtons, and distance would be in meters. So if we combine it this way, that's a Newton meter, and that's a joule. So dimensionally, it makes sense that we don't have anything in here like a squared or a square root or a 1/2 even, like some of the things that we have in here. And it just works perfectly well with the units. So that's really the biggest reason. We also need to remember that we can calculate the force of kinetic friction with the equation mu sub k, which is the coefficient of kinetic friction times the normal force. And d, again, is the distance over which the force of friction acts. So EDIS is really one of the only ones of our math models where sometimes we're going to have to calculate a little something, the force of friction, before we can actually calculate EDIS. And to calculate the force of friction, we often need the normal force first. And you know that sometimes the normal force is fairly straightforward, but it can get to be a complex calculation just to find the normal force. So, sometimes EDIS really makes things more complex. But moreover, energy that is dissipated because of friction is kind of different than the other storage mechanisms. And that's because there really are 2 kinds of forces. The kinds of forces we're talking about with EE and EG, those are what are known as conservative forces. Conservative forces are said to be path independent. And that means that it doesn't matter how they get from point A to point B. It only matters that you started at A and ended at B. Think of some of the examples that we've talked about, like going around a loop and those kinds of things. If we're only using conservative forces, it only matters where we start and where we end, all right? Not how we get there. Path-independent forces store energy, and therefore you have potential energy functions with them. They conserve that energy. So these are things like force of gravity and the force exerted by a spring. Now, friction, however, doesn't work that way. And it's because the amount of EDIS depends on the distance. So the further you push something, the more dissipated energy you have. And therefore, how you get from point A to point B is going to be important to figure out how much energy is dissipated. So friction is one of what are known as non-conservative forces. Yes, not very original, but still. These are forces that are not conservative. In other words, they are path-dependent forces. And usually they are ones that are associated with dissipating energy that's no longer useful to the mechanical system. And forces of friction fall into that category. So we kind of have two different kinds of forces. Now really how this is going to manifest itself is just in what kind of problems we can solve with these. You're going to see in our next few examples that we do in the next few days that when we only have conservative forces, when there's no friction, when we can assume frictionless situations, that we can look at much more exotic kinds of motions. When we deal with non-conservative, path-dependent forces, when we have to know how it gets from point A to point B, well, and then we have to know more about how it moves. And those are going to be the more straightforward things, like pushing a box across the table or dragging something across the floor. They're not going to be going around loops and roller coasters and those kinds of things. So it's a lot more fun to use energy with only conservative forces. So I hope you enjoyed this development of eDis. That leaves us with one and only one math model to make tomorrow. And that is, how do we calculate the amount of energy transferred into or out of a system by means of an external force, otherwise known as work?